Hi, thanks, Ben, for the very kind introduction. And as you mentioned, I'm currently a postdoc at the University of Notre Dame, and I'm doing actinide chemistry with Peter Burns and Amy Hickson, more specifically mechanochemistry. We're not going to get into that today. I'm going to talk a little bit about my own research at McGill, focused on real-time monitoring of milling reactions, but I'm also going to highlight some of the more general advances in mechanochemistry and the community recently. And so I'm going to go ahead and get started. Oh, there we go. All right. And so mechanochemistry has really emerged in the last little bit as something that has gotten kind of a lot of attention within the chemistry community. And so, in terms of really, it's something that I think is really interesting to the broader chemical community and has a lot of potential. So, in terms of today, I think we can all get a little bit excited about mechanochemistry. I'm going to introduce what mechanochemistry is. I'm going to really try and break things down in terms of the mechano part of what mechanochemistry is, as well as the chemistry. I'm going to highlight a lot of different examples that both we've worked on, as well as other examples in the literature that I think are really important. And we're going to talk about what factors are important in ball milling reactions, which is the area of mechanochemistry that I specialize in. And then what we're really going to talk about is looking at mechanochemical reactions in real time and what's known as in situ. And so what I'm really looking at is, for these reactions, which we do in a ball mill, how do we look at them in real time while the ball mill is running without opening up what's known as milling jars? And we'll get into the details now. But I wanted to kind of start a little bit with, some of the hype that's around why mechanochemistry is interesting and why it's popular. These are some highlights that have come through over the last few years, as mechanochemistry is a really powerful technique for potentially creating greener and more sustainable chemistry. And it's been recognized also by IUPAC, the International Union of Pure and Applied Chemistry, as one of the 10 chemistry innovations that has potential to really change the world. And if that's the hype, then today I want to take a little bit of time to look really as kind of the man behind the curtain in terms of, what research is actually happening and how are things working kind of in the sphere, and what level of understanding do we have. And even with the hype that was talked with mechanochemistry, there's a really important sentence here in the part where they talk about that we're, as scientists, still struggling to understand how the process works, especially on the molecular scale. And so today I want to talk a little bit about, why is mechanochemistry kind of like such a useful and potentially interesting and important technique, but also the struggles that come along with trying to understand this technique. And I'm really going to try and highlight recent advances in mechanochemistry and our understanding of mechanochemistry. And so we're going to start right at the top, very simply. What on earth is mechanochemistry, right? What are we talking about here? Well, let's start with the definition and we'll get more concrete from there. So it's defined as a chemical reaction that is induced by the direct absorption of mechanical energy. And so starting from that definition, there's actually a lot of chemistry that can really fall under it. And so if we think about, well, you have this mechanical component, the mechano of mechanochemistry, and then obviously the chemistry itself. But there's actually a lot of fields of chemistry that involve mechanical forces and chemistry itself. An example being tribochemistry, where surfaces are rubbing together. This is super important in things like understanding wear and tear in something like a car engine and other mechanical processes. You have increasingly responsive devices, so things like polymer mechanochemistry, mechanophores, where if you stretch, for example, a polymer, you can have a mechanical component which either comes apart or can come back together and do things like self-healing polymers. But the part that I'm really focused on and going to be talking about today is this idea of doing chemical synthesis using ball mills. And the idea here is that we're going to do chemical reactions instead of in a flask or in a beaker. We're going to do them inside one of these ball mills. So why would we want to do that? Well, let's first talk about how we normally conventionally do chemical synthesis. So in solution, this is probably what you're most familiar with when you think of chemistry, is that you have something here in a beaker and you're mixing things together. and you put those on a hot plate, or you heat them up and stir them and make sure they stay mixed. But there's actually a lot that goes into doing this type of chemistry. And one of the things, especially in the inorganic community where I've done a lot of work, is that, for example, for a metal, in order for chemistry to work in solution, you have to get things to dissolve. And so often if you're working from a metal salt or something like that, let's say like a nitrate, could be from aluminum to titanium, nitrate salts, chloride salts. Well, you don't naturally obtain metals in this form. As minerals, they're coming in as oxides or carbonates and things that are not soluble. And so first we have to do a bunch of chemistry in order to get something like a metal salt to even be able to dissolve, so that we can then react our two starting materials here in solution. So we have to dissolve them again in our solvent. We have the chemical reaction that we want happening, but then we still have all this solvent around. So this solvent has to be removed in order to ultimately generate what we often want, our solid products. And so it's really interesting. We're starting with a solid precursor and we're generating solid intermediates, but we're doing all of this in solution. And what this means is we're generating a lot of waste, and we're generating a huge amount of solvent and energy that's required to process the chemistry itself. But in reality, if we're starting from solid materials and we're ending with solid materials, can we do these reactions in the solid state? And one way of doing this is mechanochemistry and specifically ball milling. And what I want to highlight here is, from a practical perspective, we're taking our solid starting materials, we're putting them in one of these shaker mills. These three circles denote a ball milling reaction. We take basically a plastic jar, or it can be made out of steel or Teflon or basically any material. We load ball bearings inside, and then we just shake it. And so we have our starting materials here that you can see the two chemicals. We have our ball bearing that's loaded, and then we fire this up in the shaker mill, and you see the ball goes around and crushes these solids together. And the idea is really, can we do chemical transformations this way without the need for gallons of solvent that is at the end of the day going to be waste and requires a huge amount of heat to bring it up to the required temperature. And we can do a huge amount of chemistry with ball mills if we use also a technique known as liquid assisted grinding, where we add a very small amount of solvent or material. This is going to be less than 500 microliters per gram of material. And there's other additives that we can add, as in normal chemical reactions that we can add, catalysts or salts, which can template materials. And this is really what we consider, for a lot of reactions, a greener and more sustainable way of doing chemistry. And why is this of interest, right? We've been doing chemistry in solution now for better part of 100 years. Why should we really consider these mechanochemical reactions? Well, there's a couple important practical advantages. They tend to be very fast mechanochemical reactions. And because of that, it also means that they're a bit faster to optimize often than solution chemistry. And what that means is we can design syntheses which can be highly selective and that can produce the desired product in high yields. So it's very fast, selective, and high yielding. But it's also important that, this is something that people can actually do in their labs. And it really is an operationally very simple and scalable procedure. This is something that undergraduate students can do with, an hour or two of training. It's literally, you weigh out your materials, you put them in the jar, you put it in the mill, and you hit start and you see what comes out afterwards. So it's very simple. And it's also scalable. There's been a lot of work, for example, processing of minerals, if you think of large mines, rock crushers. So ball mills are very familiar and have been created at massive, ton scale operations in order to, in that case, create finer particles. But what we're talking about is potentially doing chemical reactions with them. And the overall idea here is really to get rid of the reaction solvent that we need to do chemistry. And that in turn produces less waste, and it lowers our costs, both in terms of energy and overall production costs, because you don't have to spend the money to get the solvent in the first place. There's also a lot of points of fundamental interest in mechanochemistry. It's works particularly well for when you have materials that you cannot solubilize easily. So you have something that just won't go into solution. Mechanochemical synthesis is a real good alternative method for doing chemistry on these types of systems. It allows us also, we're seeing more and more reports in literature of chemical species which are not stable in solution. So this is something that falls apart when it's exposed to a solvent, but so often we can make it using mechanochemistry because it's stable as a solid material, but not as a dissolved species. And we're also starting to see unique reactivity being reported, which I'll talk about in a minute. But really, what, I think the big take homes from mechanochemistry in terms of why it's an appealing method is that it's simple, it's fast, and it's generally more sustainable, at least for a lot of examples, than solution-based chemistry. So I'm going to give a few examples of some kind of interesting mechanochemical reactivity. One that's really come through recently is this idea of mechanoredox, which I think is super interesting, where you ball mill a piezoelectric material and use that to do single electron transfer reactions. And I think, this field is just recently, one of the first reports was in 2019. So this is, brand new kind of chemistry, which I think is really interesting and has a lot of potential. I really like this example here of a previous speaker, Ross Kobe, has isolated some beautiful tin complexes that he was able to isolate and characterize using ball milling, but he found that they fell apart in solution very quickly. So I think this is a good example of how we can use ball milling to access chemical species that are not possible from solution reactions. And finally, like I previously mentioned, here's some nice examples of starting from insoluble reagents, something like a metal oxide, which is this example from Tomislav Frižik a few years ago, as well as now large organic molecules which are not particularly soluble, and these have potential relevance in things like photovoltaics and other kind of organic electronics. But in terms of getting back to one of the challenges in mechanochemistry is understanding what's going on. And in solution, methods for understanding the mechanisms of reactions are relatively well understood. And that's an area that, we're really still trying to figure out how do mechanochemical reactions work. And kinetics are a really important tool in terms of understanding these transformations. And so some important factors which we want to consider when we're thinking about ball milling syntheses, we kind of, again, have these two components. We have the mechano component of the mechanochemistry, and then we have the chemistry. And so what factors do we have to consider in terms of what's going to affect our selectivity, our reaction outcome, how much conversion we're getting, and how long? Well, obviously, the type of mill that we use, as I previously showed, there's several different type of ball mills out there. You can have these attritors which rotate around, where basically you think of it kind of like a stir with a bunch of balls in it. You can have this shaker mill, which I've shown, which is what we do all of our chemistry in, or you can have what's known as a planetary ball mill, and they work well at different scales. But basically, the type of mill you use and the size is going to affect how much impact force the sample is getting, the temperature and things like that. You can vary the amount and size of the milling media, the balls basically within the actual milling container itself. Again, this is going to change the forces applied and the temperature of the overall reaction. Obviously, most of this mechanochemistry is now done using automated mills, and like any motor, you can make it go slower or faster. And so how does the speed of the ball mill really affect the chemical reaction? Another thing to consider is what type of material you're going to use for ball mill. Milling jars can be made out of steel, Teflon, ceramics. There's multiple plastics out there, even stuff like sapphire can be used. And the real question, this can be really important if, for example, you don't want to use steel if you have something that's going to react with metals. You might need something that's chemically inert, like Teflon, let's say if you have strong oxidizers in your system. But, all of these factors, they're not only going to, enable potentially chemistry, but they're also going to change potentially the kinetics and the behavior of the reaction. And then obviously, what we're also really interested in is how long, should we mill mill something for in order to know that the reaction is done. On the chemistry side of things, the ratio in terms of our reactants and reagents of what we're putting in, you know, what is the ratio, is something that's very important in ball milling. You don't have bulk solvent space where, you know, an excess of a reagent can just sit dissolved. And so if you have excesses, they have to be somehow reacted either in the actual chemical reaction itself, or they're going to remain as a solid impurity. So you end up with only a solid phase. So this can be really important for directing also the outcome of reactions. There's been a lot of research in this area. And then often we use both liquid and solid additives. Liquid additives, again, that's liquid assisted grinding, is really important in terms of also controlling the reaction outcome. We've also got solid additives. And then finally, the reaction temperature, just like in solution chemistry, this is going to be really important for both, you know, the yield and making sure your products don't decompose and things like that. So I'm going to look at one of these factors, and we're going to go kind of through a number of them just with some examples. This is not research that I did, but this is some great work by the Stuart James group up in Belfast. And so what they did here is they took zinc oxide, which is, again, a nice insoluble metal oxide. They're reacting with the imidazole, and they're basically tracking the rate of disappearance of this protonated imidazole using Raman spectroscopy. And they're doing this, then they're milling at different frequencies. So in this case, that vibratory mill that I was showing you before, the shaker mill, which is going side to side, is oscillating at a frequency of 10 hertz. And then in the fastest speed, it's 25 hertz. And what's interesting there, they stop this reaction after a certain amount of time, and they basically take the sample out and they analyze it using Raman spectroscopy, and you get these second order kinetics. And what you see is that the change in reaction rate is really not linear when it comes to change in milling speed. So doubling the milling speed does not double the reaction rate. And this isn't super surprising, but this was a really nice kind of starting point in terms of, you know, the community was starting to look at, okay, so how can we get kinetics and use this data to better understand how mechanochemistry works? This is one of my favorite papers. If you're into mechanochemistry, I think this is a fantastic paper by James Mack in Cincinnati. And he tackles a lot of problems here. And I think it's really cool. So what you're seeing here on the left side is he basically took a reaction, or they took a reaction of dienes and dienophiles. So this deals all the reaction, and they know the relative energies, which they calculated by DFT, of these different reactions. And then what they do is that they mill it for basically a certain amount of time, and they're looking for basically the activation energy versus the yield. And so basically when these processes have low activation energies, they're getting 100% yield. But then for some of the reactions, they're only seeing partial conversion in I think the 30 minutes or the 1 hour time frame of milling, and then eventually leading to no conversion. But they went further with this, and they started looking at different materials like PTFE here, Teflon or stainless steel, and at different milling frequencies. And here you can really see that actually the material that you use has a pretty significant impact on the actual rate of these transformations. The most dramatic here being at 18 hertz, where, you know, hardened steel, you're getting 60% conversion, but if you do the reaction in Teflon, you're getting only 5 at this point. So I thought this is a really nice example of showing both the effect of frequency as well as the materials that we talked about that you can use in ball milling, and how that might affect your reaction kinetics. And so in this case, you know, if you need to be running the reaction Teflon, you'd have to either go longer or somehow impart more energy into the system by increasing the milling frequency or something like that. And I think one thing that always comes to mind with mechanochemistry is so, you know, if you start to look at kinetics, how does this compare with processes in solution? And this is another paper by Stuart James, where I think he did a really great job of looking at this Knoven-Nagel condensation reaction. And here's the plot. Here in blue, you have the solution kinetics, which is, you know, pretty standard kind of exponential growth. But if you do the exact same reaction mechanochemically, excuse me, you get this sigmoidal shape. And this is something that we see multiple times, and you'll see more in the presentation. And I think one important thing to realize is this is very common in mechanochemistry, but it can actually have it can signify different things mechanistically. And I'll show some examples of that. And this is something that they obviously realized too. And they said, well, there's a couple possibilities here that we could investigate. Water could be acting as basically, which is a byproduct of the reaction, could also catalyze it as kind of this water-based autocatalysis mechanism. They added more water to the reaction. They saw that isn't what caused it. They also said, well, maybe this is a particle size reduction effect. As you mill for a couple minutes, your particle sizes might be getting smaller, and so reactivity goes up over time. They pre-milled the reaction mixture, and they found no difference for small particle sizes. They basically pre-milled each reactant individually, mixed them together, and didn't see a change in kinetics. Or it could also be due to internal heating. And in this case, they were talking about due to reaction exotherminescence. Your reaction is releasing heat, and the heat is then driving the reaction, and that's why you see this acceleration over time. They changed the temperature, and they didn't see huge dependence on that. And so in this case, what they're actually kind of ended up describing it as is a change of reaction rheology. And so basically you have, again, this mechanical component and this chemistry component that they found that this turns into a gum-like phase, and that somehow the reaction propagates much faster through there. And I thought this is a really nice example of the difference that mechanochemistry and solution chemistry really are, like how kinetically different the profiles look for what otherwise is the same reaction. And so this kind of brings me into the theme of a lot of the research that I've been working on the last few years, which is the idea of monitoring milling reactions in real time. So how can we get kinetic data from these reactions while they're occurring? So first of all, we don't want to stop the mill, and we want to acquire data in real time, and ideally with good time resolution. And the idea here is, can we gain a mechanistic understanding of what drives these solid state ball milling reactions? And from a practical perspective, can we use that then to optimize reaction selectivity, try and get conversions up, as well as minimize the amount of reaction time necessary? And then finally, it's also of interest because if you're looking at this data, you have the possibility of identifying new phases and novel structures or intermediates that you might miss if you're just looking at the endpoint of the reaction. But I think the ultimate goal here is really to enable efficient scaling and enabling new chemistry. So if we understand the fundamentals of how a mechanochemical reaction works, we can more efficiently scale the process, and we can also, use these insights to potentially develop new chemistry and more efficient things like mechanoredox reactions. So how do we do this? There's three main techniques that I've worked with. There's a couple others in the literature, which I'll briefly mention. But the main one is powder X-ray diffraction, where we're looking at the crystallinity. Now, remember, we're doing our reactions in the solid state, and they're largely of crystalline materials. So we can actually use powder diffraction to monitor the reaction, which is something you can't do for solutions because it's dissolved, and so your material is not going to be crystalline. We can also use Raman spectroscopy to look at the vibrational information. And this vibrational information can be really, really useful for looking at the different species and different compositions, even if you have a reaction mixture that's not very crystalline. And finally, one of the things that I've spent a lot of time working with is fluorescent spectroscopy as another means of getting some electronic information and trying to understand what's happening in these reactions. In terms from a practical perspective, how do we do these measurements? Well, powder XRD, these measurements require synchrotron, so we have to go, we've done most of these at the DESI in Hamburg or the ESRF in Grenoble, France. And the idea here is very simple. We take a slightly modified ball mill where we basically have jar sits above the mill, and we put our milling jar in here, just like you saw in the video in the introduction. We load our sample, load our milling balls. We have this shake side to side. But in this case, we have the X-ray source of a synchrotron, which is shown here. It's coming out of this tube, which is here. And we shoot the beam through the milling jar and collect the diffraction signal on the detector. And this gives us information of what the crystalline phase is at any given time during the reaction. We can also use fluorescence and Raman. Now, the nice thing with these is these are lab setups that we can have in our, just benchtop setups in our actual lab. And so here we have a probe-based Raman spectrometer. And so basically the laser comes in, shines through the milling jar, and collects the signal back. And in the case of fluorescence, we're in this case using also a laser as our excitation source. And we have a fiber optic which collects the fluorescence coming back into a spectrometer. And so I'm going to walk through a couple different systems where we use these kind of in situ techniques. One of these is for the synthesis of metal organic frameworks. So in this case, this was some early work I did in 2016. We're taking dihydroxy terephthalic acid, which is a MOF linker, with zinc oxide. You mill the two together and you basically get MOF74, which is a nice coordination polymer. It's a nice MOF, has hexagonal channels, really beautiful structure. And you get 2 waters as your byproduct. And so when we do this in real time, what you're seeing here is these are the PXRD patterns on top. So this is the simulated pattern from MOF74. This is the diffraction pattern for this 1D chain polymer, which is reported in the literature. And when we look at the diffraction signal over time, I'm going to show a lot of these waterfall plots, as they're called. And what you're looking at is the time axis goes up here. So we're starting at 0, going to 45 minutes. And this is the 2 theta axis, or the diffraction angle. And so what you see over time is we're just able to basically line up the simulated diffraction patterns with our experimental data. And you see that we get these 1D coordination polymers for about 20 minutes, and then you really get the emergence of the MOF74 under grinding with small amounts of liquid, in this case, water and DMF. One thing that I think is really important to note, and this we found was actually really interesting, if we switch this liquid-assisted grinding phase all of a sudden to 20% water and 80% DMF, we actually see that the reaction slows down quite a bit, but we're also now seeing the formation of an intermediate phase, which we have not been able to identify. So again, we start a reaction here, we finish the reaction here, we see the same 1D chain polymer where only the carboxylates have reacted with the zinc, but now we have this unknown intermediate phase, which unfortunately we weren't able to get the structure of, which then subsequently converts to the final MOF74 structure. And this is actually, in terms of behavior, quite typical of what we see with a lot of milling reactions. And you know, to kind of follow this up, this is not work that I was directly involved with, but came out of the Frigid group a few years ago. When we did these X-ray diffraction measurements, again, in this case, making a ZIF MOF, so this is with an ethylamidazole and zinc oxide, we noticed, again, we get these stepwise progression of different phases happening. In this case, what you see, the progression is known as the row phase, the anaphase, and then finally the quartz phase. And we did a bunch of calorimetry and thermodynamic calculations, which basically show that we're actually going down in energy. So we're starting at the least stable phase. So you can think of this as the kinetic product, and we're basically going down the energy ladder into the thermodynamically favored product. And so this is a way of kind of rationalizing a lot of the behavior that we're seeing. Is we're not somehow defying thermodynamics or doing anything crazy here. We're seeing different phases, and we're basically trapping kinetic products as solids, forcing them to crystallize, because there's not this bulk solution reservoir where things like nucleation can happen without much propagation. And so I think this is a really nice example of kind of rationalizing that you're going to get often a stepwise behavior of phases, and that this is basically due largely to thermodynamics and the thermodynamic stability of the different phases. We've also looked at some areas such as thermal monitoring, and this is, again, not primarily my work, but something that I was involved in, where we then, a wireless thermocouple was embedded into one of the milling jars, and we ran the in situ X-ray diffraction. In this case, the axes are flipped, so you have time going this way and a 2 theta degree. But and on top here, we have the temperature. And so we're able to read the temperature with really high resolution and quite high accuracy through basically a metal plug, which is in contact with the inside of the milling jar. And what's really interesting is that you see a pretty rapid and significant increase in temperature. And this is due to frictional heating, right? You have this mill, you've got balls inside of it, everything's rubbing together, you're getting a bunch of friction, so the temperature goes up. And eventually this friction basically equilibrates with the heat loss to the environment. The room You're starting at room temperature at 25 degrees C. Eventually, the jar equilibrates at about 32, 33. So frictional heat is going to go with the heat loss. And then you have the heat of the actual reactions. But what was really interesting, at least in this case, and I think this is partially because the change in energy of these phase transformation isn't huge, is that this frictional heating is going to be highly dependent actually on the sample that's in the milling jar. So if you think about it, frictional heating, the question is how inelastic or how elastic are your collisions and how much heat is being absorbed. If the material, your sample, can absorb a lot of the energy of the milling process, the temperature is actually going to be higher. And I thought this was quite interesting and really quite striking. You can see the increase in temperature here. And then as soon as this second phase nucleates here, the ZIF8, you actually really can see that the frictional properties of that phase are lower, and so the temperature itself drops. And so by looking at the thermodynamics and some of the energy calculations in this work, they were really able to show that actually it's this frictional heating term that really dominates for these types of reactions. Now, if you were to ball mill highly exothermic reactions, obviously the reaction heat can come to dominate the frictional heating. So there is a bit of an interplay there. But for most chemical reactions, most normal chemistry that's not super exothermic, it's actually going to be the frictional component that plays a huge role. One of the work that I kind of did subsequently, looking kind of at temperature, we did this very kind of simple condensation reaction, just grinding these two together. Now we're not adding any liquids in the transformation, just an amine coupling to make this quinoxylene and water as our only byproduct. This is a super nice reaction, gives a great signal, and we get quantitative conversion with no observed byproducts. So it really is wonderful chemistry. We can look at that now using Raman spectroscopy. So again, these are plotted using waterfall plots. The idea is going to be the same. We have a lot of background due to our PMMA jar, which we're using. So we can get the Raman signal of the reactants when they're not in the same place as basically the PMMA bands. But what we end up doing is we usually find a region where we get good Raman signal of all of our reactants, and we don't have a lot of interference from the PMMA, and we're able to actually get this Raman signal. And I can talk about the processing if anyone's interested, but I'm going to kind of skip that and say, you look at this, you can track this signal of the different components, and that you can get then the kinetics of the reaction. And so right now we're looking at the formation of the diphenyl quinoxylene at different milling frequencies. So in this case, at the bottom here, we have 20 hertz, and then we're just increasing by 2.5 hertz. This is the milling speed, the oscillation speed of the ball mill. And what we see is we're starting off with linear kinetics, and then eventually we get something it's sigmoidal. It looks kind of exponential, but it really is sigmoidal. And there's a lot of noise here at the beginning because you don't get as much sample in your beam path for Raman. So this is a bit of an artifact, but the rest of the curves are actually reasonably accurate. And one thing that we did with this also is then, again, now I'm just looking at the temperature at the reaction endpoints, but we suspected the temperature might have a pretty significant role here. And so again, we're not hitting any crazy temperatures to get the reactions to go. The highest that we measured, I think, is about 42 degrees Celsius in the milling jar after this hour long of milling. So, it's not generating massive amounts of heat. And we're only about 10 to 15 degrees Celsius, or maybe close to 20 above room temperature when the reactions finish. But we thought this change in kind of the kinetic profile was really interesting to look at, right? And what might be causing that. And so we were really thinking that, well, the temperature changes here are quite small, but are they significant enough to kind of change the chemistry? And so to explore that, we took a pre-milled reaction mixture. So we basically took the two components, we milled them for 30 seconds, put them on a hot stage, and then applied a linear temperature ramp. Now, this isn't quite the same profile that you expect in milling. It's slightly more exponential, but, as a kind of first order approximation. And what we saw, which was quite interesting, is if you line up here, you start to see, again, sigmoidal reaction kinetics. So again, we just take this, we heat it, and then we're just constantly taking Raman spectra every 10 seconds or so. And what this suggests is that, you know, this could be really, it's probably thermal that's driving this type of sigmoidal behavior in the case of the high annealing frequencies. And actually, if you look roughly as where this sigmoid is starting, you're in the 40 to 50 Celsius range, which is exactly the temperature that we're starting to hit when we're milling at higher frequencies, and we see this kind of sigmoid. So in this case, I think this is really strong evidence, and it actually is known for this reaction that there is a deep eutectic which can form. And so I think we're not at the eutectic point yet. We don't see large scale melting. It goes in as a solid. So this is before and then after heating. So this hasn't completely melted, but we seem to see this like kind of slow transformation near the eutectic point. In terms of another possibility that, you know, was discussed in literature is this idea of kind of autocatalysis, especially water autocatalysis. And in this case, this was a project that I worked on looking at some ionic co-crystals that are, you know, interesting as fertilizers. So in this case, we're trying to make calcium urea phosphate. And so we're doing that by reacting calcium, either calcium hydroxide or calcium carbonate, with an equivalent of urea as well as an equivalent of urea phosphate. When you make this, you know, the water, your byproducts are either going to be water or water and one CO2 if you're starting from the carbonate. And one thing that I was quite surprised when we originally ran this is X-ray powder diffraction data. It's a similar waterfall plot. But what I'll point you to here is this is the calcium carbonate reaction. And what I want to point here is when we do the refinement basically of this data is for us to reach half weight conversion basically of our co-crystal is taking 30 minutes for calcium carbonate, whereas, you know, we're really getting fast conversion in 3-4 minutes here using calcium hydroxide. And this really struck us in the data. It says, why is calcium hydroxide so much faster than calcium carbonate? And so actually this was the synchrotron data we took, but we wanted to do more experiments. So we then moved to Raman spectroscopy in our lab, where we were able to do a lot more experiments. And using some new sapphire jars that we developed, you're actually able to look at this reaction reasonably efficiently and get the kinetic values. Oh, excuse me. Something stuck in my throat. But anyway, so what you end up seeing here is this is the kinetics for the calcium carbonate, and then here's the kinetics for the calcium hydroxide. And we started to notice if you add a small mixture, you're dramatically accelerating the rate. And since water is the byproduct of this reaction, we went to the idea of, well, maybe water is autocatalyzing this reaction. So it's the product of the reaction, but it can also catalyze potentially the transformation, which makes sense because it's acid-base chemistry. So you have hydroxides and hydronium ions. But what I think is striking is the amount. In this case, we took calcium carbonate, and at a 200 milligram scale, we added 2.5 microliters of water, and we have a massive change in the reaction kinetics. And furthermore, if we take our calcium carbonate data, we can fit it to an autocatalytic rate law. And for the middle portion, in essence, this part here of the data, it nicely fits an autocatalytic reaction rate law. So we found that this is really one of the first kind of detailed kinetic evidence that this water autocatalysis is a thing in mechanochemical reactions, and that it's very important in certain reactions. One of the more recent projects that I did near the end of my PhD, well, actually throughout my PhD, but it's finally just got posted on ChemArchive last week, actually, so I'm quite excited to talk about this. Here, we took a pharmaceutical, indomethacin. So this is an API. We're co-crystallizing it with saccharin to make this indomethacin saccharin co-crystal using liquid assisted grinding with methanol. And in this case, we were trying to use fluorescence to monitor this transformation because indomethacin is fluorescent in the solid state. It's extremely poorly fluorescent in solution, but this co-crystal is actually quite fluorescent. And we're actually able to monitor this reaction using fluorescence as well as Raman at the same time. And if we line up the fits that we get, we're seeing, reasonably good agreement depending on how you kind of process the data between the fluorescence profiles as well as the Raman. And so this is a really, fluorescence can be, for fluorescent materials, obviously, can be a really convenient, low cost way of monitoring mechanochemical reactions and getting kinetics. But one of the things, co-crystallization is obviously important for making stable forms of pharmaceutical ingredients. But one of the big challenges in looking at mechanical processing of pharmaceuticals, so when you compress something into a tablet using machinery and stuff like that, is the presence of amorphous phases and transformations of polymorphs. And the reason for that is you can have a single material, in this case, indomethacin, but it can have different crystal structures. And those different crystal structures can have dramatically different pharmaceutical properties. So, for example, the release profile or the bioavailability can change. And so it can really affect how basically effective the medication is. And so when you process pharmaceuticals, you want to be very careful and that you have the right crystal structure. And amorphous phases are really tricky. And the reason is that they're they're inherently thermodynamically unstable. And so they tend to relax to different phases. And so we can start looking at this in ball milling reactions. And we think amorphous phases play a really significant role in milling processes, but it's really hard to look at because they're not crystalline. And so you can't use diffraction-based techniques to really get very much information about them. And so we turn to spectroscopy. And in this case, we can actually use Raman spectroscopy as well as fluorescence to look at this transformation. And so if we take gamma indomethacin, which is the thermodynamically most stable product, we continuously grind it, we start to see the pretty significant and rapid amorphization to get an amorphous phase, which is, so the gamma form is shown in this trace here in blue, the amorphous form is shown here in red. But what's interesting is that when this amorphous phase relaxes, it actually converts into the alpha form. And this is which is a less thermodynamically stable relative to the gamma. But we're actually able to monitor this conversion in real time. And so we can actually see here gamma indomethacin is, the amorphous. And it's interesting that we have this dynamic where you have the amorphous as well as the gamma phase, which are coexisting for a time. And then all of a sudden you kind of have this almost like nucleation of the alpha form, but it doesn't completely convert. We still have a lot of amorphous indomethacin. And where these in situ techniques really shine is by the time I take this reaction out and do any sort of characterization, the end product is always 100% alpha indomethacin. So this amorphous phase, which is formed by the mechanochemical basically means in the reaction, relaxes so fast that you can't really characterize it by looking at the end point of the reaction. So this really shows where in situ techniques can be really powerful in terms of understanding, the mechanisms of what's happening and looking at things like, are there amorphous phases involved in these types of transformations? And how are they interacting with materials while they're being, ground in the ball mill? And fluorescence is more difficult to fit and interpret. So one of the challenges we have is we have these nice crystal materials. With diffraction, it's very easily to correlate, okay, this signal belongs to, this crystal structure, we know what it is. That's more challenging for these spectroscopic techniques. And so Michals, a computational chemist who was with Thomas Love and is now a professor in Poland, did a lot of the computation for us in order to see if we can model the actual emission behavior. I just want to very briefly show, using periodic density functional theory, we're actually able to take the crystal structure and model the fluorescence. So we can have that using only spectroscopic measurement, we can really start to look at, getting insight into the structure of the materials that we're monitoring. And we're getting quite good agreement with these models here from the HOMO-LUMO transition. The other thing that's really interesting is we can start thinking about what's happening fundamentally. This figure is a little bit complicated, but I'll do my best to explain it. In red here, this is going to be the total energy, and in blue we have the oscillator strength. Well, what we're looking at here is this dihedral angle. between this carbon, nitrogen, and then carbon and oxygen. And basically that conformation plays a huge role in the overlap of the HOMO and the LUMO. And as you rotate this dihedral angle, you're going to have different configurations, and those are going to change in energy, but we can also look at the change of the oscillator strength. And that oscillator strength basically correlates somewhat to or strongly correlates with the emission intensity of the molecule. And what we actually found is that if you look at this, near the bottom here, in terms of total energy, there's relatively low oscillator strength, so we wouldn't expect things to be very fluorescent, which is actually seems to be the case for example, in solution, you'd expect most of your molecules to have this type of conformation that's going to be non-emissive. However, in the solid state, if you look at this angle in the crystal structures, we're here. And so all of a sudden, we're higher in the total energy of the bond itself, but that's being stabilized by the crystal structure. But we're also considerably higher on the oscillator strength. And we think this helps explain and rationalize using computation some of the behavior in terms of why the fluorescence is increasing under, in the solid state and under the transformation. One of the other factors that we've looked at in terms of ball milling is looking at a change in crystallite size. This is something that always really surprises people, that you can make crystalline materials in a ball mill. And it's very kind of counterintuitive, because usually you try and smash crystalline materials and get them amorphous, like I previously showed. But if you're using liquid assisted grinding, you're actually able to make really, really crystalline materials. This is a synthesis of a MOF called UIO66 from this zirconium hexanuclear cluster with this terephthalic acid linker. And what I found was really interesting is you get nice diffraction patterns of the MOF forming. And Lucia did a bunch of Rietveld analysis and using the Scherr equation was able to estimate the crystallite size. And one of the things that I think is really important to note in the synthesis is that the crystallite size is increasing of this UIO66 phase as it's forming, but then it becomes relatively stable over time. So for liquid assisted grinding reactions, you don't actually have to worry that, oh, if I'm going to grind for an extra 30 minutes after the reaction is completed, you probably won't degrade the crystallinity of some of these harder materials, such as metal organic frameworks. So with this, this is the work that I kind of presented. I also want to do a quick shout out to some of the other work that's been out there that I have kind of no involvement with. But Ivan Halas and Kruno Uzarovic at the Institute of Ruder Bodzkovic have done really, really interesting work using these in situ techniques. This is one of my favorite things in terms of finding intermediates. Here they're making these palladium azobenzene complex, and they actually get these CH insertions. But what's really interesting is that they can actually see the different steps of the reaction for organometallic complexes, that they see the adduct of where the nitrogen is coordinating to the palladium. They're then seeing the mono insertion product before eventually going to the dipallidated species. So this shows really, and here you can see the adduct, the mono, and then dipallidated traces using Raman spectroscopy. And so I think this really shows the power of the methodology for seeing honestly stepwise transformations in chemistry in the solid state, which I think is fascinating. Franziska, the Emmerling group in Berlin, Germany, has done really also interesting work. They do a lot also with thermography instead of embedding a thermocouple, just reading the digital image. And they've done a ton of really cool work with in situ. So I really wanted to emphasize that we're not the only ones doing this. And they get these really interesting multi kind of step reactions, and they can actually see water release and different materials, basically these different phases they go through. They can also see it in the thermal data for thermography. And they've done, like I said, at least 10, they've got really great papers on this topic. So if you're interested, I would highly also recommend checking out both the work coming out of Ruder Bodzkovic and Franziska Emmerling's work. So I just want to briefly summarize what I've talked about tonight. what can real-time monitoring tell us? It can tell us the phases that are appearing in different reactions, including intermediates, and help us start looking at exploring different phases and their stabilities. It can really tell us how different milling configurations and how milling speed can change our reaction kinetics and reaction behavior. It can help us look at and try and understand the role of temperature in these reactions. Is this driving a change in kinetics, or is it just slightly accelerating the reaction, or is the change in reaction rate really not that temperature dependent for the system? Is something else driving the reaction? It's done a lot in terms of helping us look in terms of the role and selectivity of liquid additives. So whether it's water catalysis or changing the reaction outcome, by changing the grinding, the liquid assisted grinding, you're getting a different product. And then finally, I think we can really start exploring this idea of crystalline versus amorphous reaction components and things like crystallite size and nucleation processes, which are basically impossible to measure without a real-time technique. And I think this has a lot of promise for looking and understanding chemical synthesis in the ball mill. And then finally, just as a more general conclusion, I hope that I've convinced those who maybe need any convincing that mechanochemistry is useful, and often it's a more sustainable way of doing chemical synthesis. It's broadly applicable, and in situ monitoring is broadly applicable to a lot of different systems. We can look at organometallics, MOF chemistry, organic chemistry, API pharmaceuticals, biomass. There's a lot of different chemistry we can look at, and that we're getting really interesting kinetics, and that those kinetics can really help us with the understanding the mechanisms of these transformations, as well as find intermediates and optimize our reactions. And I think what's also really important is to emphasize that, we've got a lot of different mechanisms happening. Mechanochemistry doesn't just operate by one mechanism. And I think it also requires diverse reaction monitoring techniques. The more chemistry we can do by mechanochemistry, the more ways we need to monitor it. And in terms of outlook, I'm going to finish up here on maybe a bit of a high note. I think really the most important thing, I think mechanochemistry is a really bright future. I think in situ monitoring has a very bright future. I think we've got a fantastic and growing global community of people interested in mechanochemistry, and I think that's the most important thing of all. I'm seeing mechanochemistry. It used to be, when I remember started doing it in undergrad, it was this fringe thing, and it seems now everyone seems to at least know about it. We've got a lot of new techniques coming out. Zanes and NMR have only recently been published in terms of in situ techniques. There's some really cool papers on those I'm happy to share if you're interested. Alternative to ball mills are being explored. So, looking at, how are reactions occurring in things like twin screw extrusion, as well as resonant acoustic mixing, which are also, mechanochemistry, but they don't rely on this ball milling aspect. Instead of hitting things with balls, you're either extruding them through screws and grinding them together, or this is just mixing really fast without the need for the balls, which is really interesting. And I'm seeing a lot of computational methods. I think there's a lot of interest in using computational work to better understand these types of processes. With that, I want to thank all of you for your attention, for sticking it out so late. I know this is it's quite late, and thanks for coming. And I have to really thank Thomas Lefragic and the whole group and everyone at McGill for all their help and support, as well as everyone at the synchrotron and our collaborators, as well as our funding agencies. And with that, I'm happy to take any questions. I'd love to answer them. If you're interested in the topic of in situ monitoring, there's some reviews. There's one that's a little bit dated at this point. That was one of the original ones when these techniques kind of first got described in 2015. There's also a book chapter, which has really recently been published by Adam Michalchuk and Franziska Emmerlich. And so I highly recommend those if you have any interest. And if there's any other interest, always feel free to reach out to me either by email or on Twitter. So thank you.
All right. Fantastic talk. I think that one was a hit. So we will go ahead and just jump straight into the questions. So the first one here is, how do you ensure that you're actually collecting signal of your powder? So I think that this was like the powder X-ray, or even I guess the Raman as well. Is there something that you do in particular to make sure that you're actually having your sample pass through, or I guess pass through long enough to get the spectrum?
Yeah, so this is definitely a challenge. One of the things is if you have like a small beam, we generally end. So if you think of a jar as just kind of a cylinder, you tend to aim at the bottom part just because things obviously fall down, and so there's usually some material there.
Mm-hmm.
But you do get basically because of that an arbitrary fluctuation in your signal intensity at least, and so everything we look at has to be relative. So the absolute intensity you can't really use to track most chemical reactions, with the exception of fluorescence. If you illuminate everything kind of at once, it seems to work okay. But for Raman and stuff like that, so it's a lot of kind of alignment in terms of that you're on the right kind of part of the jar. And then it's just understanding that the signal's a little messy. You can deal a lot with it using post-processing techniques. There's a lot of data analysis, whether it's in writ for X-ray diffraction, if you want to get those traces out, or for the Raman stuff, I've done a lot of fitting, and I have my own scripts that I use in MATLAB to normalize everything. But it's definitely possible. So,
are there any techniques that are similar to like when you do transition or transient absorption spectroscopy, right? Like you have, you take a few measurements in the ground state and you average those, and then you have a few measurements in the excited state and you average those, and the difference is sort of what you get out. Is it the same idea? I know it's not quite as clean because it's not necessarily as even, but is it the same idea?
Kind of. Well, so what I mean with the post-processing is, so the signals are fine. It's the intensity that varies arbitrarily, and so everything just has to be normalized in some sort of way, shape, or
okay,
form.
I got you.
And how you do that is a little bit tricky, and it depends on the data, in all honesty. Mm-hmm. But that's usually how it's done. And so things like internal standards or relative proportion become very important.
Okay. That makes sense. I can see where it would be a tricky thing to do for sure. What's the time resolution on these? Like for the, let's say, the powder XRD.
Yeah. So the XRD measurements we require every 10 seconds.
Okay.
Raman we run either at 5 or 10 seconds. It depends on the spectrometer, and the sample and how much data we actually want. Okay. But you get good time resolution with fluorescence and Raman, especially, and even if you have a very crystalline material and you've got a lot of sample, you could probably get that down. But we're really in the second range. For fluorescence, you could go a lot faster. But the problem with fluorescence is you have to interpret it, yes. Which is hard.
Yeah. Okay. Let's see. So we've got a question here. So I think this was in reference to the zinc MOF work that you showed, where it went from your starting materials to the 1D structure to the actual MOF by the end. And the question is, does the 1D structure actually go away at the end? Because it looks like the peaks for that 1D structure were still there. If it is it possible to make it completely go away if you were to mill it for longer, or is there some basically limit on the reaction such that it's always some amount of the 1D structure will always be there?
No, we get basically quantitative conversion coming out of that reaction. So this is actually funny. I actually presented, so the one that I have in my slides are the original data. We had a referee for that paper originally say the same thing. And this is kind of a funny story, but we ended up having to retake the data, and we did. And there we just ran it for an extra 30 minutes. And you see that the 1D polymer really does go away completely. And so the data sets, in essence, have been kind of truncated. The reaction's not quite finished. But yeah, it does go away. We get beautiful powder patterns. You can check the paper if you want to see them. And so that we didn't have too many issues.
Is that generally pretty true for the mechanochemistry? Like if it's a reaction that can go to quantitative yield, or I'm using the wrong terms because I'm not I'm not a chemical engineer. But are you generally able to drive the reaction all the way to an endpoint, or do some of them end up at like a limiting step where like you there's only so much of the reaction that you're going to be able to make happen?
Yeah, I mean, it depends on the chemistry, obviously, but in general, if you optim, and sometimes mechanochemistry can require quite a bit of optimization, but for a lot of systems, you can really get quantitative conversion out of it. So that's really what we aim for. That's what I aim for with most of my work. Because otherwise you end up with a kind of nasty separation problem sometimes of doing your purification. And I think it's now more accepted to say, yeah, you can make it mechanochemically and then purify it using, something like a column or recrystallization. But I remember when we started in the field that people said, well, if you're going to recrystallize it or with solvent, then what's the point of doing mechanochemistry? So we really worked quite hard to get quantitative or as close to quantitative as we could get. And it actually works remarkably well with a lot of milling reactions. Obviously, it depends a little bit on the chemistry, but it definitely can. And for basically all the examples I showed for the in situ, we usually pick systems that basically go quantitatively.
Okay, yeah, that makes sense because that makes it a lot clearer in terms of trying to track the reaction.
Yeah.
In terms of the optimization, can you talk a little bit more about that? Like, what's in general, what are the conditions that you look to change to try and optimize it? Like if you were going to say like, all right, I'm gonna go with this one first, then this one, then this one. What's your general order?
So yeah, generally there's if we're thinking of optimizing things, so the milling speed we basically set it at max at 30 usually, because you just want things to go unless you think you're decomposing. But in terms of time, you can sample it at different increments, maybe 30 minutes an hour. But the big things controlling the reactions that I've found so far, the stoichiometry of what you're putting in is super important. And especially organic and a lot of coordination chemistry, you work in solution, people say like, oh, I've got a 10-fold excess of this reagent. That doesn't really work mechanochemically because that reagent is just going to sit around. And so there's an advantage there because you need less reagent, but there's a sensitivity to the kind of ratios of what you're putting in. The composition of the liquid additive, if you are using a liquid additive, is extremely important. But I have had some success in just mirroring what works kind of in solution. Sometimes if they say, yeah, this reaction works best in 50-50, DMF, THF, or whatever you're using, often that will translate into mechanochemistry. And so that is super important. In terms of time, I usually try and kind of pick one time point. Maybe it's 30 minutes if I think the reactions are fast, or 60 or 90. And then I run all my reactions at that point, and I try to optimize for the different kind of ratios of reactants, different liquid additives, things like that.
Okay. Let's see. Does the milling jar material make a difference in the kinetics? So this was when you were talking about tracking the temperature of the reaction, and you were able to see, when you went from the starting point to the product, the temperature kind of showed a rapid drop and all that. If you used a metal jar that transferred the heat away more quickly than the PMMA, would that affect whether either the rate of product formation or actually being able to form the product?
Yes, absolutely it would, but I will say it's also complicated because you're changing the mechano aspect of it a lot. So the actual impact forces, the shear forces, and all that. So that's what makes it a little bit. That's one of the issues in mechanochemistry. You can't isolate the mechanochemical forces or the mechanical forces from the temperature very well because of the friction issue. And so that's, I think, a challenge. So the temperature wise, that'll definitely have an effect, but then you also have the change in forces and the hardness of the material, which will also have a pretty significant impact.
Oh, okay. So it would probably change the temperature effect, but then maybe because of the mechanical effects, maybe you still get the same result or slightly more or less the same result or something like that.
Exactly. If you want to think about it, like, for example, if you're in Teflon and it's a better insulator, but it has a softer impact. And so, maybe when you switch to steel, the temperature goes down, but the reaction rate actually goes up. And that can be because the impact force that you're imparting on the material has gone up a lot.
Okay. Interesting. Let's see. We got a question here. Has anyone worked on computationally modeling the amorphous phases?
It's hard. So this is a problem I think that's beyond kind of mechanochemistry in my research. I think this there are people who are looking at starting to model computationally amorphous phases, but it's in and of itself a big challenge. That's different than mechanochemistry. But yeah, I think there's a lot of interest, and I think there's a lot of promise in that area. I think the computational methods are getting there.
Okay, that's a good thing. Let's see. Does the mechanochemical energy uniformly distribute the energy, or are there some types of atoms or bonds that are more susceptible to cleavage?
Yeah, well, I mean, in any molecule, there's going to be some weaker bonds, and in theory, those can cleave first. But it really depends, and so this is what's difficult in especially ball milling. You're not applying kind of a normal uniform force to the molecule, like maybe you would be in polymer mechanochemistry, where you have two ends of the same polymer. You've got your mechano bond, your mechanophore in the middle, and you pull on the two sides, and it pops apart or comes together. In that case, you're really controlling the forces. With ball milling, it's pretty random. And so generally what would happen is the thermodynamically weakest bond, or whatever is exposed, will generally react. But also it's important to remember that, these are solid crystalline materials, so the actual stabilization of the crystal structure has a huge role to play.
Okay, that makes sense. So I'll encourage any final questions to come in. I've got one as well. This one's not directly related to the talk, but I think this is just one I'm curious about based on the sum total of all the mechanochemistry talks that we've gotten, including yours. In terms of reaction possibilities, is there anybody that's doing work with basically with gases? So like you have some starting material, you either purposefully put gas into the milling jar, or in the course of the reaction, the gas is released, and you take advantage of that to do some other reaction along that's something that you intentionally want to do, or just are interested in following. Is there any work like that that's being done?
Yeah, there's some. It's generally been more focused in the inorganic area, I will say. So you can buy milling jars that you can load with compressed gases and flow. Air-free chemistry has obviously also been done. You can actually, even using pressure gauges, monitor some gas evolution reactions by mechanochemistry. And in the, I think, 80s, 90s, and early 2000s, there were several people who looked at really strong nitrogen absorption onto, these are almost like self-propagating reactions. So they're almost like explosions where you get titanium nitride synthesis, just really hardcore, you're grinding at 200 degrees. This thing is sparking, and, the temperature is going up.
Okay.
There's been some work in those types of reactions, in terms of you have some nitrogen or other gas that then gets reacted in. The other obvious one where there's been work done is things with carbonates, with gas evolution of the CO2. And you can monitor that using pressure.
Interesting. Okay.
So yeah, that is totally viable to do with mechanochemistry, and people have kind of done that, but I can't say that there's been a ton of research in that area.
Okay. All right. I was just curious.
Yeah.
So I think that's all the questions we've got. So if anybody has any final ones, get them in real quick. But otherwise, I will go ahead and say thank you to Patrick. So this fascinating talk. You've done some really cool work, and I'm sure you are continuing to do cool work. Like I told you earlier, I really hope we'll get you back at some point in the future to learn about what your ongoing stuff is.
Great.
It's really, this was a fascinating talk. Great job. If I can get you to hang around for just 1 minute, we'll talk very briefly.
Sounds great.
To everybody,
thanks everyone for coming out.
Yeah, absolutely. Thank you for coming out. Have a good weekend. Be safe. Get your boosters if you need to. And we'll see you here again next week. Next week we have, let's see, who is it? Diana Ramirez from Universidad Iberoamericana, Ciudad de Mexico. And so I'm sure it'll be another great talk. And have a great night, everybody. We'll see you next week.
Have a great night. Nice to see you, Ross. Nice to see you, Isaiah. Thanks for coming out.
Yeah.